Welcome to the latest session within the Xendee University Week. And as you might have realized already, we are talking today with utilities. We had a session with the New York Power Authority early on. And we talked a lot about microgrids this week and had a lot of great conversations. And we were thinking that actually we gave our friends from the utility space the last words here in this conference. And this is why we have also this great presentations today. The first one coming from SMUD and the second one from PG&E. But let me start here with Sophie Tongsopit and her colleague Gabriel Leggett, both from SMUD. And Sophie is an accomplished energy policy and distributed energy systems expert with more than 20 years of experience spanning utility strategy, clean energy policy research, and program management across the United States and Southeast Asia. Currently serving as a senior strategic business planner at Sacramento Municipal Utility District, SMUD, she develops business models and programs for distributed energy resource, microgrid screen pricing, and customer-side renewable energy solutions. Her career includes a leadership role at the California Energy Commission and an expert role at the California Department of General Services, UC8 Clean Power Asia, UC Davis, and Thailand's Ministry of Energy, where she had lead initiatives focused on renewable energy deployment, energy storage, and regulatory innovations. So I believe Sophie will be the main presenter, but maybe Sophie, you want to introduce Gabriel a little bit, and then I hand it over to you. Thank you.
Thank you for the introduction, Michael, and thank you, Xendee, for inviting us to present in this session. I'm joined by Gabriel Leggett, who is a principal engineer in grid modernization, and he's going to be covering the engineering challenges of the pilot project that we will share today. So the project is called Community Solar and Electric Resiliency Project at Grants Union High School. A little bit about SMUD. SMUD is a community-owned, not-for-profit electric company serving the Sacramento region in California. We've been around for about 80 years now, and we're governed by a 7-member elected board of directors who set our rates and establishes our policy direction. SMUD is one of the cleanest utilities in the nation, with more than half of our power coming from carbon-free resources. We also have an ambitious goal of zero carbon emissions by 2030, which is anchored in reliability and affordability. In fact, our customers' electric bills on average are more than 50% lower than our neighboring utility. The project that I will be covering today is part of our broader Sustainable Energy Communities Initiative. It is still in a planning stage. So several years ago, we learned that the Sacramento metropolitan region is ranked near the bottom in terms of growth, prosperity, inclusion compared to nationwide cities. In addition, reports predict that the Sacramento region is vulnerable to intensifying climate impacts in the form of extreme heat, severe storms, flooding, smoke from wildfire. So these impacts will fall the hardest on the underserved communities. So these findings prompted us to address the disparities of the under-resourced communities that we serve, to make sure that our communities are resilient and no communities are left behind. So in 2018, SMUD launched the Sustainable Communities Initiative, environmental equity and economic vitality to all neighborhoods in our service area. So the microgrid that we'll cover today at Grants Union High School is expected to support a community that is vulnerable to intensifying climate impacts while also promoting innovation in the microgrid space. And because we want this pilot project to be a win-win for the community as well as the utility, We overlaid a sustainability heat map and a map of substations that need mitigation. What the sustainability heat map does is that it collects key data to inform decisions about where resources should go within our communities to reduce growing economic disparities in Sacramento. And for the substation map, which we cannot show here, we identify substations that would be overloaded and require additional investment in the next 5 years. And Grants Union High School is located in that ideal location where there is a good intersection between economic disparities and substation needing upgrades. It is located in Del Paso Heights neighborhood, where 30% of children live below poverty line. So we partner with Twin Rivers Unified School District for this project to provide clean energy for community members, dispatchable batteries to support SMUD's grid during constrained peak hours, and a microgrid system to power the school's gym and stadium as a shelter during prolonged power outages. In addition, the solar canopies in the parking lot of the school will provide shaded parking to reduce urban heat islands. So what is unique about this microgrid is that it is located in front of the meter. So during normal operations, the solar system would export 100% of electricity to the power grid, and that electricity will be distributed to income qualified customers who live in the vicinity of the school through our residential solar shares program, which is a community solar program. The battery system, which is also front of the meter, is part of our commercial virtual power plant pilot or VPP pilot. The batteries will discharge energy during peak hours in response to DERM signal. All the assets will be controlled by SMUD's Distributed Energy Resources Management System, or DERMS, and the DERM system will send their head schedule to the batteries to direct charging and discharging. This allows us to have full control and make changes in real time in response to grid conditions. And during power outages, the solar and battery system will island together to support continued operation of the school's administrative areas, cafeteria, some classrooms, gymnasium, and stadium. 1 second here. So here's how the benefits will be distributed to different stakeholders. For the community, the microgrid will support the operation of the Electric Resiliency Center, which will be activated by the American Red Cross during prolonged power outages or emergencies. Now, if we were to design this system in order to support the Resiliency Center only, most of the time the solar and the battery systems would be on standby to provide backup service, but that will be very expensive. So we thought about how to fully utilize the solar and battery system as grid assets. That is why we locate the systems in front of the meter and use it for our community solar program, which will serve our under-resourced communities. And the batteries provide multiple values to SMUD, including peak load management, energy arbitrage, and resource adequacy value. But together, all these two values are not enough to cover the cost of deploying expensive battery. So to turn the economics positive, would require an additional value stream that can be found in the form of substation deferral value. As part of the commercial VPP pilot, a portfolio of batteries can be used as non-wired alternative to reduce peak loading on a substation and hence defer the cost of upgrading its capacity to cope with distribution system load growth. So the whole system together serves as a tool to reduce costs for SMUD system as well. In terms of innovation, this microgrid offers an opportunity for SMUD to learn about the front of the meter microgrid design, operation, and control. We'd like to create a standardized utility control solution during on-grid and islanding conditions. This will also serve as a bridge to future use cases such as vehicle to buildings and multimeter microgrids, where many customers serve advanced. We use
So maybe there's a clarification question. Is the battery also in front of the meter, or is the battery behind the meter? Because you mentioned that the PV is in front of the meter as community shared, but I'm not sure if it's clear where the
yes.
battery sits here.
So the battery is also in front of the meter,
So
and it will
everything.
dispatch directly
Okay.
into SMUD grid. Yes.
Okay.
Yeah.
Okay. Thank you.
So the only time that it serves load is during islanding. So we use Xendee to simulate islanding conditions during outages. What we found is that the current design can help the system ride through outages on hot days in the summer and the fall. We also tested the worst case scenario in the winter when solar becomes less available. And we found that solar and battery alone would not be adequate. And Gabriel will talk about how we might deal with this as well as other engineering challenges. So I'd like to pass the mic to Gabriel.
Yep, thank you, Sophie. Before I start, I just wanted to know that I originally worked at Xendee Gas and Electric doing microgrids. I transitioned to Pacific Gas and Electric working a remote grid. And now I'm here at SMUD doing battery energy storage and also working on this front of the meter battery and solar microgrid. So I'm going to focus on some of the challenges that we are going to face specifically for this project, and then just kind of challenges in general for microgrids. So the biggest one we have for this front of the meter system is that the solar and the battery systems are being installed by two different companies, and we're trying to coordinate with both of them. And the reason why we need to have this coordination is because there is concern that we're going to have over generation of the solar when we are islanded. And once the battery reaches 100% state of charge, it's going to disconnect and we're going to lose the microgrid. So this is just a big concern that we have. So there's a couple ways to mitigate this. One would be to have a direct communication, so fiber optic or just having radio communication with the power plant controller and the solar inverters. So to tell them to curtail as we approach 100% state of charge. Another option, and this is something that Pacific Gas and Electric did, is to utilize the frequency watt and volt var curves built into smart inverters. And you can have the battery system increase the voltage, increase the frequency, for example, like say 60.1, 60.2. And by increasing frequency, you can have the inverter respond to that by decreasing its output. So there's going to need to be coordination between the battery manufacturer and EPC at the end for commissioning to ensure that the solar system will not cause the battery to go to 100% state of charge, and then we'll end up losing the island. So the other concerns we have specifically for this project is that Sophie had pointed out. During days where we have multiple rain events or it's very cloudy, we're probably not going to have enough solar generation, so we're going to have under generation, and we may be unable to support a multi-day outage. What we're planning on doing is installing basically a generator plug and a place to hook up a roll-up generator, which would be either propane or diesel, to provide generation during those moments. And so we're already going to have the infrastructure already put in place. That way, it doesn't take us, half a day to go in and try and land connections to their electrical panel. There's already going to be a connection for us to plug into. So those are the two big concerns about this project right now. In general, for microgrids, I would say the first question is, are you going to do a seamless transition or are you going to do black start? So I've worked on both. So to do a seamless transition, you really need to have an advanced relay that will detect a utility outage and not wait for voltage and frequency to go to zero. You have to detect that you are going into an outage. So at Xendee Gas and Electric, what we did is anytime we saw a frequency deviation or a dip greater than 2 hertz, we would assume that we are going into an outage. We would send a signal to the power plant controller to convert the battery inverter from grid following to grid forming. And then we would only see potentially just a blip in power as we transitioned over, and that would be seamless. There is a little bit of tuning that is required, so the commissioning process takes a little bit longer. Black start is easier because obviously you'll just wait for the grid to go away. The customer will go dark, generally wait about 5 minutes, and then you start up and perform your island. You isolate and then you start up. Concerns there are inrush and magnetizing current. So if you have motors or transformers that you need to energize, the inrush may be too much for your battery inverters, and you can have an overload. This is something we experienced at SMUD's first microgrid, our solar port microgrid. So a way we combated that was to do a voltage and frequency ramping. So we ramped up voltage and frequency slowly over 5 seconds. That reduced the inrush current. And from there, we were actually able to magnetize or provide the magnetizing current for the transformers, and then to energize and island the site. Moving on to fault detection. So as we know, for IBRs or inverter-based resources, if there is a fault, inverter-based resources do not provide the same amount of fault current as traditional generation or the utility. So you have to build in a new fault detection. Something that we did at PG&E would be a voltage control over current. So when you do have a line to ground fault, voltage will collapse, and current will slightly increase, maybe about 10-20% coming out of an inverter. So what you can set is that, hey, if I see a voltage dip of, say, 30-40%, or 0.3, 0.4 per unit, you can say, I want to trip within a few seconds if I see a continuous current 10% above continuous current. And that has been an effective way to detect faults when you have just IBRs that don't provide large amount of fault currents. Even then, you still could have miscoordination with your downstream breakers. So there's always a concern that there's a fault with a microwave, on a 15 amp breaker. That's not going to coordinate well with your 100 amp or 200 or 400 amp breakers, and you may lose a large part of your microgrid. So there is work needed to be able to have correct coordination for protection. Last one would be anti-islanding protection. This is something that SMUD's very concerned about. We want to make sure that the grid forming device is not feeding back into our grid. A couple ways you can do it is have an automatic transfer switch that's certified, or just have a paralleling device, usually a SEL 651R or 751 that has a sync check. So it won't allow the breaker to shut if you have voltage and frequency on both sides, just to ensure that you're always islanded and not feeding back to the grid. And that's just for safety for our workers.
A couple of questions here, maybe for clarifications, because this is very detailed. I mean, I have to say this is great stuff. But there's a question from the audience, also from my side. I mean, Sophie, you said, well, everything is in front of the meter, right? And then you said when there's an outage, the battery is feeding the load, right? And now with all the conversation with Gabriel, I'm not so sure if I fully understand, or also some of the audience, if it's in front of the meter, if it's behind the meter, or, I mean, what is it really? I mean, are you changing it? Great.
Yeah. So it is front of the meter. This is actually unique. So it is in front of the customer meter, but still on the secondary side of the utility transformer. So imagine the transformer going from 12,000 volts down to 480. So we're at 480 on secondary, feeding the customer meter at 480. We're tapping in between the customer meter and the secondary side of the customer transformer. So we are going to install a paralleling device on the secondary, which I haven't done before, actually. I've either energized on the primary and fed through the primary transformers, or done a behind the meter system, or some kind of combination of that. So this will be the first time I have a secondary voltage paralleling device for a full front of the meter microgrid system.
Okay. Yeah, and I'm not sure if you see the Q&As, but there's also a person really telling you that this is great work. So I just want to relay this if you don't see it. So with this, sorry for the interruption, guys. So
thank you. And thank you, Gabriel, for going over microgrid engineering challenges. The rest of the presentation, I'll talk about other types of challenges as well as future vision for this pilot project. So there are challenges related to design, operation, and replication. In terms of the design, we'd like to have a business model that is a win-win for everyone and balances the three pillars of benefits. Of course, we want to be as innovative as possible, but that's really expensive. And there are competing interests between the site host and the utility. Like Michael is concerned, the site host wants some benefits of bill savings or peak shaving benefits from the batteries. They may even want resilience. But from the utility's perspective, we want to maximize the dispatch during peak hours. So how can we design a business model that leverages these DER resources to benefit the site hosts, the customers, and the community? And in general, the site hosts would want some types of benefits. And if they don't get bill savings, they would want some kind of compensation. So the business model has to be designed to ensure that is a win-win for everyone. In terms of product offering, you heard about our community solar program, residential solar shares. This is for underserved communities, low-income disadvantaged customers. And because the systems are very expensive, we have to find a way of shouldering the cost. So we use our green pricing mechanism to enable some customers that are willing to pay a little bit higher for zero carbon and community benefits to help sponsor the project. In terms of operation, as you heard, this is all new to SMUD, and we still have to develop a new interconnection rule and guidelines for customer-sided front-of-the-meter configuration, as well as establish operation and emergency procedures. In terms of replication, the current pilot is located at a high school site. Other types of site hosts may require different types of benefits from a solar plus storage system, which makes it hard to replicate this business case. And because the school campus is very conducive to many kinds of innovation and experimentation, ideally, we would need a microgrid design that is flexible enough to allow integration with future options such as bidirectional electric school buses and network microgrid. So for bidirectional electric school buses, these are great resource for complementing the stationary battery. You can imagine that during an outage, maybe the battery is almost out energy, and then we can bring in electric school buses to plug into the microgrid and in order to extend operational hours of that microgrid, especially during extreme climate events. For network microgrids, because this school site is located in an area where there are a number of nonprofit organizations that have an interest in electric resilience, it's possible that in the future we can network all those microgrids together and take advantage of a model called networked microgrids, where the resources are shared for economies of scale. And these are examples of nonprofit organizations in the area that have an interest in resiliency that we could partner together in the future. And finally, there's a broader vision regarding resilience within our own organization. Different people think about resilience differently. And especially when you go into the communities, they also have a different perception of resilience. So beyond electricity, resilience could mean the ability to prepare and recover from climate disasters. It could also mean creating a clean energy workforce pipeline. So the pilot that I discussed in this presentation is for the first phase only. And if funding becomes available in the next few years, SMUD can try to achieve a broader definition of resilience. It could mean working with our community-based partners to fund economic empowerment activities and building a pipeline of clean energy workforce. And that's all I have for this presentation. We welcome the questions from the audience.
Thank you, Sophie and Gabriel. And I'm really happy about this presentation because there was so much talk during this week about behind the meter projects, right? And this is very unique. And I mean, I tried to follow Gabriel as well as I could, but there's a lot of stuff going on. So I'm really thankful for this presentation. There's a question from Chuck. Curious how SMUD ended up with different companies working on the PV and battery separately instead of single integrator. I'm not sure, maybe you can say something about this.
So that is related to how we developed the commercial virtual power plant pilot that started before this pilot project was put together. So those companies that are working on the pilot, they are already, trying to make this type of model happen. So we brought that in. And then for the solar system, we had to bring in a different company because the existing companies for the VPP pilot do not have a focus on solar. So we wanted to bring in like really, and we compare different prices to get the highest value for the solar system.
Okay, thank you for this. Another question regarding business model. I'm not sure if it's clear if you're providing cost reductions to your clients, or because at some point you said willing to pay a premium for CO2 reduction, but then at the same time you're also reducing cost internally. So are you providing that school with some reductions on the bill, or is it really mostly on your side?
Yeah, so it's mostly on our side, and those who are willing to pay premium are other customers within SMUD's territory that are paying already for our Green Energy program.
Okay.
Which is a voluntary program where they pay a little bit more. And
it seems like you're financing this completely internally through your clients, right?
We self-finance this pilot project.
Yeah.
And we try to recover the cost through other customers.
Perfect. Okay. Really nice presentation, Sophie and Gabriel. So now I want to move over to the last presentation in the Xendee University Week, which is now from PG&E, from Alan Escoriza. He's an expert in grid innovation with Pacific Gas and Electric Company. He's supporting the micro design and delivery team. He has over 14 years of experience spanning the electricity, utility, distribution, energy resource, and energy efficiency domains. He's also a licensed professional engineer. His work focuses on advancing PG&E's community microgrid portfolio in delivering resilient energy solutions for critical facilities and communities across the PG&E service territory. And I believe Alan is also going to talk about this community program today. In his current role, Alan provides technical leadership and program support for community microgrid projects, including those funded through the Microgrid Incentive Program. His responsibilities include technical consultations with local communities, coordination with third-party developers, and close collaboration with internal PG&E teams spanning planning, interconnection, system protection, operations. So with this, Alan, I want to give you the honor for the last presentation of Xendee Week, and I'm looking forward to the Microgrid Incentive Program.
Thank you, Michael. Sophie and Gabriel, excellent presentation. That was really good information. Thank you for sharing. So, as mentioned, I will be talking about the Microgrid Incentive Program. I am a grid innovation engineer at PG&E. I work on the microgrid design and delivery team. And so what are we going to cover today? We're going to start off with just some basic, let's get on the same page about what a community microgrid is. Then we will talk about the Microgrid Incentive Program. We'll talk about the project stages. Then I'm going to spend a little bit of time talking about the studies that go into these microgrids. And then we'll conclude by sharing additional resources. So when we're talking about a community microgrid, what are we talking about? So if we look at the image on the left, we see a boundary in black, right? A polygon. Within it, we have these dark blue lines, which symbolize the PG&E distribution lines. And then we have a local generation site within that boundary. These generation resources would be owned and operated by a third party. So the applicant to the MIP program would own these, but PG&E would own and operate the distribution lines. Within the boundary, we're going to see critical facilities, items like hospitals, police and fire stations, gas stations, and markets. And these orange dots that we see here, these symbolize isolation devices. They can be reclosers or switches. And essentially what would happen is if the main grid were to go down, these isolation devices would open and they would isolate the community microgrid from the larger grid. And the customers within it would be able to continue to receive power that is sourced from that local generation site here. All right, so let's talk about the microgrid incentive program. First off, what are the goals of it? So the microgrid incentive program is designed to fund clean community microgrids that support the critical needs of vulnerable populations most likely to be impacted by outages. And we're talking about front of the meter resources here as opposed to behind the meter. So the goals of this program are to increase reliability and resiliency for critical public facilities. We want to prioritize communities with higher portions of low income, access and functional needs, and electricity dependent residents. We want to enable communities with lower ability to fund development of backup generation to maintain critical loads during outages. And also a goal is to provide an opportunity for testing new technologies or regulatory approaches to inform future action to the benefit of all ratepayers. All right, so let's talk about the funding that is available. Per award, an applicant can receive up to $18 million in incentives per project. This $18 million would come from two programs. There is so in the middle of the image, there is the CMEP funding. CMEP is the Community Microgrid Enablement Program. And here, applicants can receive up to $3 million per project in what's considered a microgrid special facilities allowance. So these are costs that would normally be covered by the applicant. And this funding would cover the costs associated with a microgrid islanding study, which we'll talk about later, and costs associated with equipment to enable that safe transition and operation in island mode. Think items like isolation devices, reclosers, protection devices, the utility microgrid controller. The other bucket that I want to talk about, let's talk about the one on the right. This is through the MIP program, and this is for the interconnection allowance up to $1 million per project. This money can be used towards the interconnection study costs, also known as the system impact study, and any costs or necessary upgrades that are identified as a result of that study. The larger bucket in funding is here on the left. This is up to $14 million per project. So here we're talking about the application incentive request, or AIR, and these funds can be used to purchase the equipment. So your front of the meter equipment, your batteries, your solar, let's say you're doing wind, whatever your resources are. It can also be used towards engineering and project management costs, and also for property lease or purchase costs. Now, we understand that the development of a microgrid incentive program application can be costly and time-consuming. So MIP will reimburse the cost of an eligible application up to $25,000. And this is whether the applicant is awarded a grant or not. Notice that I've underlined the word eligible there. So the project in the application must be eligible and meet certain requirements. And we'll talk about what that eligibility criteria is. All right. So who can apply for the program? There are essentially 3 categories. On the screen right now, we see 2 of those. So MIP-funded microgrids must serve communities that are considered both susceptible to frequent outages and a community that is considered disadvantaged and vulnerable. So let's focus on the category on the left, the frequent outages. There are 4 items listed there. One of these 4 must be met in order to be considered eligible. And things that are being looked at there have to do with fire risk, history of outages. Is it in an earthquake risk zone? I do want to note that on the bottom, we do state that local or tribal government leadership may be able to justify other forms of vulnerability. So if for some reason the project does not meet any of those 4 criteria, there is another approach there, and that'll be taken project by project. Now, moving on to the category on the right, disadvantaged and vulnerable. This is looking at the income levels. Is the community a California Native American tribal community? Is the area listed as a high risk according to the Cal Enviro screen? Is the community in a rural area? And similarly here, if none of those 4 category or items are met, but the microgrid powers a critical facility that primarily serves one of these groups, then the project may be eligible as well. Now, let's talk about the third category. This has to do more with the technical side of it. So the project must meet the eligibility requirements of a tariff, the CMET tariff, Community Microgrid Enablement. The project must be able to island for a minimum of 24 consecutive hours. It can island for 48, 96, but at least 24 hours. And the project resources must interconnect at a distribution level. So a distribution line that is 50 kV or below. And there are certain emissions related criteria that must be met. All right, let's talk about the project stages.
Alan, sorry,
yes.
That's a question. Can you go back 1 slide? Oops, here we go. Why above 50 kilowatts? I mean, what's the reasoning on PG&E side that you want to have this not in a lower voltage level?
It's part of the program. Some of the just by definition, that's what our tariffs in our program or criteria is. So these community microgrids are typically 12 kV. So we're going to see a lot of that, but we just have that cutoff for 50 kV and below. So we're not going into the transmission side. Good question.
Okay.
All right, so the creation of a multi-customer community microgrid is a complex endeavor involving the community, its technical partner, and PG&E. The projects will go through a 5-stage process. So stage 1 has to do with the consultation, so getting initial information, preparing the design. Stage 2 has to do with the application submittal. So submitting an actual package. We'll talk a little bit more about what that consists of. And then PG&E reviewing the application for eligibility, doing some screening, and then execution of a grant agreement. Stage 3 has to do with the studies. That's the interconnection and the microgrid island study. Stage 4 has to do with the development and commissioning. And then stage 5 is the operation. That's for 10 years. So stage 1. In the consultation stage, we're looking to meet with the potential applicants and identify what the resiliency needs are within the community. We'll discuss potential solutions, review eligibility requirements for the programs, and we will help them prepare the application or gather the information that they need in order to prepare their design and submit an application. As part of their application package, applicants will submit information on the applicant, the project, and they will include several attachments. I have not listed them all here, but just as an example, some of the attachments would be a single line diagram, 30%. We understand that this is still early on. Some geospatial maps that show the microgrid boundary, the proposed site where the generation resources would be located, and the locations of the isolation devices. There will be a microgrid sizing template that will be included as the application. This template is where PG&E shares what the load would be for that microgrid. It is forecasted out, and in that template, that's where the applicants can enter information about their project resources. There will also be a budget and schedule template and a resource description document, which includes spec sheets, quantities, all the details there. And then we will require some engineering analysis documentation to be submitted, as well as some information related to permitting and site access. All right, so let's talk about these studies. There are two critical sets of studies that are undertaken. The first one that we'll talk about is the interconnection study, also known as the system impact study. This determines the necessary upgrades and requirements to safely interconnect any new DERs deployed as part of the microgrid. Separately, the microgrid island study, the MIS, is required to ensure the operational safety and stability of the community microgrid during the islanded operations. In some cases, we will approach these studies in parallel. In other cases, we will do them in series. It will depend on the project specifics and any of the risks that are identified early on. The microgrid islanding study relies on detailed information about the generators, the interconnection to the grid, and the microgrid circuit itself. What this scope can consist of, and it'll depend on the project specifics, but the scope may include a base model development and validation. Once that base model is developed, then power flow and voltage analysis, and some protection studies, black start and load restoration, power quality, transient stability studies, hardware in the loop testing. Again, that will be on a case by case. All right, so additional resources. I know I shared a lot of information here about the programs and what the projects could look like. We do have a technical best practices guide for community microgrids. And when we have parties that are interested in applying for this program, one of the first few things that we will do is we will point them to this document because it gets really into the weeds about the electrical design, how to size the grid forming generators. We'll talk about the transitions, seamless versus break before make. We'll talk about the development controls, commissioning, and what goes into operating the microgrid. So I highly recommend this document. There is a link here for those that are interested. Anyone also feel free to reach out to me via email. I can share that. And the other resource I want to share is the Microgrid Incentive Program Handbook. You can find that at pgne.com/MIP. And this guides applicants through each stage of the MIP process, from the application to development. So if you are interested in learning more about this, I would definitely take a look at this handbook. All right, so there are two email addresses shown on the screen: communitymicrogrids@pgne.com. Feel free to reach out to them for any questions. And you have my email there on the right. I welcome emails as well. And now we have some time for questions, if there are any.
Thank you, Alan. A great overview of the program. Very much appreciated. So let's go to a couple of questions here. And the first and the obvious one is this only for PG&E service territory, or can other people in California do this also? So maybe
great question. Yes. So it is in PG&E territory. So if the meters and the customers are in PG&E territory, then the project is eligible. Unfortunately, if it is not in the area, it cannot be part of the program.
I think it's not part of the PG&E program, but if I understand it correctly, other utilities in California offer this too. I'm not sure about if it's similar, so maybe you know how they do it in Southern California. Maybe you know how our colleagues have, if they have a similar program and it looks very similar to this. I don't know. Yeah,
so this is the Microgrid Incentive Program. Specifically, that one is it's a statewide program. It was authorized by the CPUC. It includes about $200 million in funds. There are 3 utilities that are participating. So in addition to PG&E, if you are in SCE territory, you can reach out to them and they will have a program as well. And also San Diego Gas and Electric.
Okay, thanks. The other question, when developing the sizing of the microgrid, do we have to size it to the estimated load on the distribution line it will serve, and how can we obtain this data?
Excellent question. Yeah, so essentially what will happen is during that stage 1, the consultation stage, we will have meetings with the applicants to define what their boundary will be. It could be as big as or as small as 3 customers. It could also be a neighborhood. It could be a huge portion of a city. So it varies. And the load and what the resources must be sized to will be forecasted out. So an estimated load at 10 years. So in one of the slides where we talked about the stages, I talked about the operation stage, and that is for 10 years. So we are forecasting what the load will be in 10 years. We're using certain assumptions, and then we are adding some safeties in there. But yes, essentially we will provide the applicant with the load data in the microgrid sizing template that they will then use to input into their programs like Xendee or other programs to size their DERs. Then once they have those values, they will input those or some information into our microgrid sizing template, and it will do some preliminary checks and flag any items for concern.
Mm-hmm. So a follow-on question to this, because you mentioned the load growth and all this for the next years. So what about performance in this system, right? So is there anything attached to performance over the next, let's say, 10 years, 15 years, or What if it doesn't work out as it was planned? Is there any measure to mitigate this?
Yes, so there's several tests that are done periodically. So we're going to do the user acceptance testing, and then part of the agreement, one of the other agreements would be the microgrid operation agreement that will call out for periodic performance tests. So every so often we will actually have to conduct tests to make sure that the microgrid can indeed operate and support the load as it was stated initially.
Okay, thank you. Another question regarding the studies. It looks pretty extensive to some extent. So why is it that you're requiring hardware-in-the-loop testing, Alan, for some cases?
Yeah, good question. So we have found that, it was kind of mentioned earlier with the SMUD presentation that there are some challenges with inverter-based resources. So that's why it's important for us to have some of the hardware in the loop as part of testing. We want to check to see if the equipment is actually so the inverters or the controllers or relays are actually responding the way that we thought that they would in the studies. There are a lot of unexpected things that could happen. In fact, we had a situation where for a project that the inverter ended up not performing the way that we thought it would during the studies. So we were able to flag that initially and swap it out for a unit that would. So these types of studies also help prevent future issues. Good question.
Okay. And in terms of resources, Alan, are you providing at PG&E these resources, or is this all third party? Because it's not that simple to go to just do a hardware-in-the-loop testing, right? So it needs some experience, it needs the equipment. So how does this come together?
Yeah, so depending on what the equipment is, if there's already a solid model, or if it's been modeled recently by our team that is doing the islanding studies, then the hardware may not be needed. When it is not needed, we will try to go without it. However, we are trying to minimize risks. So it'll depend on a case by case.
Okay, thank you. So what I want to do is now, before I close this session and the conference, there's one remaining question for SMUD. So if Sophie is still there, there's a question for SMUD. How is SMUD currently managing solar PV overgeneration curtailment challenges? Could the pumped hydro energy storage project present a practical low-hanging fruit solution to absorb excess solar generation and hence grid reliability and flexibility?
Yeah, thank you for that question. So at the transmission or bulk power system level, we do not have enough solar resources to create the overproduction situation. So we have like a few hundred megawatts of behind the meter solar and a few hundred megawatts of large utility scale solar. So that's not a problem right now, but overproduction situation that Gabe was mentioning had to do with the fact that during islanding, because our solar system in that pilot project is a bit oversized in comparison to the customer's load, because the way we size it is to be able to purchase it for our community solar program. So the overproduction situation happens during islanding, and it's disconnected because it's connected at a low voltage distribution level. It's not that large hydro or pump hydro is not able to help.
I understand. Okay, so I think this was all the questions we had here. So I really want to thank you, Sophie, Gabriel. I'm not sure if it's still online, and you, Alan, for this really very insightful conversations. And this actually leads me just to conclude to the final step, to conclude the conference. We had 22 events this week and more than 700 registrants or attendees. So it was pretty intense for some people. And actually, some people interrupted their vacation for this. So I'm also very thankful for that. And this wouldn't have been possible with all the speakers, with you, the attendees, and of course with the really, really great Xendee team here. And the vision that we had for this event was really to bring together in a simple way a group of people which can really bring this market forward. And I hope we achieve this, and we certainly look forward to do this again. So with this, I want to thank everyone here. I want to wish everyone a good weekend. And next week, stay tuned for the recordings of all these sessions, the announcement and the announcements of the winners for the Platinum Xendee license. So thank you everyone again, and have a good weekend.